We should finish chapter 6 today, and so we'll have a test on it'll be Wednesday of next week over in chapter 6. Review what we did Wednesday of this week. We talked primarily about the control of MA. Just go ahead and start drawing it out while I'm talking about it. We talked about the line voltage compensation, which is whenever we get to the test, it's the only thing that's going to come off before you get to the auto transformer, so it's line voltage compensation. So we get to the line voltage compensation. The purpose for that is to, again, avoid the peaks and the valleys in the voltage waveform so that we get consistent feed into the auto transformer. All the names for the auto transformer, I'm not going to go through them, but you know them, right? So, and also the auto transformer, how it works, we're not going to review that either. We've done that to death. So, so line voltage compensation, first thing it gets to, and it feeds it into the auto transformer, and we've got a secondary circuit that comes off of that. So on the test, you know, just by virtue of where these things are, you should be able to pick them out, right? So you've got the MA selector as what it is that, and it's just specific, you know, levels as opposed to KVP. Both of them considered a rheostat because you can turn up and turn down. It's just that these are more, I don't know, I guess you'd call them discrete settings or individual settings that are set at, you know, like 50, 100, 200 and things like that, as opposed to KVP is pretty continuous. You can select any KVP level. So also a rheostat, that's a MA selector. It controls the current through the filament, not through the tube itself yet until we make an exposure. So we select our MA and then we send it through a step down transformer, right? And then that comes out and it goes into the filament. And the whole purpose for this circuit was to thermionic emissions, heat up the filament. Thermionic emissions works off of anywhere from 12 to 25 volts. And it works off of anywhere from 3 to 6 amps. So relatively high amperage, very low voltage, so that we don't send electrons across the tube before we're ready for them to go across the tube. Right, so the things that we talked about on that were, you know, the entire MA circuit. So on the test, it's in, you know, the textbook, if you look at the diagram at the end of the chapter, calls, you know, it has the high voltage circuit going through the filament circuit. On the test, I'm going to call this the filament circuit. Okay, just so that we don't confuse high voltage, low voltage filament, which is very low voltage, right? So this is our filament circuit. All right, so it's the MA circuit, filament circuit. It creates space charge, controls filament current. It is a rheostat. It's an MA selector. Utilizes step-down transformer to lower the KV or lower the voltage, so that again we don't send electrons early. So it works off of low voltage, 3 to 5 amps. Creates a space charge, and we talked about saturation current, and we talked about the space charge effect. So space charge effect was to make sure that we send just the number of electrons across the tube that we wanted to send across the tube during exposure, as opposed to saturation current being like maximum current tube, the maximum tube limit, right? So the greatest mass that you can send across. Then we talked about the falling load generator. It's kind of a weird place for it in all this, but the falling load generator was the type of x-ray machine that would start at the highest amperage possible, and it automatically selected your MA throughout the exposure so that it would drop throughout the exposure. And the purpose for that was to reduce the exposure time to as short as possible, right? So then we'll get any questions on that. Yeah?
So when we go to the step-up transformer, we're sacrificing amperage to create voltage. Is the opposite true for the step down?
Pretty much, yeah. So since when we go to the step-up transformer, we get extremely high voltage, we would have extremely low amperage, right? And that's why we have two circuits, one to control the amperage once we make an exposure, one to control the amperage and one to control the voltage. So if we only had one circuit, you know, and it was just, let's say, the high voltage circuit, then every exposure we made would be utilizing the 15% rule, would increase KVP and decrease mass with every exposure. With this setup, we can control each one individually. Does that make sense? Yeah. Okay, so then we talked about exposure timers, and fundamentally we had, four? We had synchronous, and we could identify synchronous from a couple of different things. One is that they're always going to be multiples of 1/120th of a second. They can only be used on single-phase machines for reasons we'll talk about here in a second. And a lot of times they'll be operated with dials. You may have buttons, but sometimes dials. So 1/20th of a second, fractions, going to be read out in fractions rather than decimal points, and may have knobs. And then we talked about electronic, which is the most common, and we get extremely short exposure times with that, so as short as 1 millisecond. They're the most accurate, and we're going to talk about that a little bit deeper when we get into imaging. Most common, responds quickest, all the good things. So then we talked about mass timers, and with mass timers, what you have is a set MA station, and whenever you adjust your mass, you're actually selecting a time, right? So MA station is usually 100, 100, and then whenever you set your mass, you're setting your time. So 100 mass exposure. Let's say you're doing a cross table lateral L spine, which we'll get into Monday. Kind of high mass, right? So 100 mass on a cross table lateral L spine would actually be 100 MA at 1 second. It'd be 1 second exposure. So we talked about that, and then we talked about AECs. So AECs, nothing but radiation detectors that are preset to receive a certain amount of radiation before sending a signal over to the timer circuit, which you'll see drawn somewhere over here on most of your diagrams. We do have one other thing that comes off right here, and that is our KVP. Pre-reading KVP meter, right? So it's pre-reading because
You don't have KVP yet.
don't have KVP yet. We hadn't gone through the high voltage transformer, right? So so when it receives that proper amount of radiation, it'll send a signal over the timer circuit to discontinue the timer. Okay, so how do you set your timers? How do you set mass on single phase machines? You adjust your MA and you adjust your KVP and time, exposure time, right? So how do you adjust your time on three-phase equipment with electronic timer? You adjust your KVP, you adjust your MA, and you adjust your time, right? So on mass timers, how do you adjust it? You just push the mass button and it adjusts your time. So using AECs, how do you control your time? Or how do you operate time? Trick question?
You click the button.
You don't. You don't. Yeah, you don't. So it's the only type of timer, this is something I didn't point out on Wednesday, it's the only type of timer that requires no manual manipulation by you. So can you affect a change in time? Yeah, you can, but unless you're using density buttons or you position in specific ways, with normal positioning, you don't do anything with time on automatic exposure control. So when you get to a question that says which type of timer requires no manipulation by the technologist, what's your answer? ACs. Don't get that wrong on the test. Okay, so any questions on all that? Okay, so after it comes out, the electricity comes out of the auto transformer, it goes into high voltage transformer. Right? We're not going to talk about the turns ratio or anything. We've kind of done that to death as well. So it goes through that. We've got one thing over here that's wired directly into the center of the high voltage side of the high voltage transformer, and that is our
Mass meter.
Yeah, MA meter, right. So after it comes out of that, now we're ready, we've adjusted our voltage, we've increased it to kilovoltage, and now we're ready to make an exposure, right? So one of those is gonna go in that side, one's gonna go in this side over here. And so far, what we've got in this diagram is alternating current, right? Okay. With that one. So we've got alternating current. We have to have alternating current to make this work, right? So we love it. We have to have alternating current to make this work. We have to make alternating current to make this work. We have to have alternating current to make that work. But once we get to this point, we don't want alternating current anymore. We have a problem, right? We don't want to send electrons from anode to cathode because it would break your filament right away. Single exposure is gone. Even if that's unlikely to happen, which is probably pretty unlikely to happen, because you'd have to get this thing to the point of thermionic emissions, right? Which, sure, you're gonna have to put a lot of mass through this to get to thermionic emissions on a big chunk of metal. But even if we don't, even if that wasn't a potential, which it is, it's a potential that it could happen. It's, you know, probably not, but it's potential. All right, so even if that wasn't a potential, how efficient is X-ray creation just in general?
Very inefficient.
Very inefficient, right? So we've got a voltage waveform that does this number, right? So if electrons go that way, but they can't come back that way, then what we do is we take our voltage waveform and we cut it in half, and we're only using half of it. So now I've gone from inefficient to half of inefficient, right? So we don't want to do that. We want to make it more efficient. So we do have machines that do this, all right, where the X-ray tube actually becomes the thing that changes alternating current to direct current. It's pulsating direct current, right? So each one of these things is a pulse. It's pulsating direct current. It's only going in one direction, but the kilovoltage on those units is high enough that that would never become an issue. So you only see that in dental machines, okay? Even mammo, or you know, which shoots generally with no higher than about 40 kVp, are still going to use rectified machines, but dental units, have y'all seen the new dental units? You know, they used to have those things that would hang down from the ceiling. They got this little Star Trek gun that they just stick up to your face now. That's wild. You know, it's just a little bitty thing that just goes zip and you're done. So in those units, okay, so let me put that on pause for a second. What do we say when we have a problem that we need to fix? You're going to do what with the situation? Rectify it, right? So we got a problem, right? At minimum, we got a problem with inefficiency. We got electricity that, you know, if it goes from here to there, we're only using half of the wave. If it starts to come back this way, there is that possibility that we could get thermionic emissions off of that and send the electrons back across the X-ray tube and break our filament. We have a problem, right? So we got to rectify it. One of the few things in radiology that makes sense is that we're going to do that with rectifiers, okay? So now we're going back to the last chapter, the chapter before, where we were talking about electricity. What we have were conductors and superconductors, and we had semiconductors, right? So semiconductors, what's going to do that? So let's start with this. Let's say we want this waveform, but we're using kVp high enough that we could send electrons back across the X-ray tube. Okay, so we got electrons going that way, but we want to prevent them from coming this way. The electrons and the voltage is coming off of this. So if we have it going in both directions, then what we've got is electrons going that way, all the way through the tube, and out through the other side, and then they're going to reverse and go back that way. Okay, so we want to eliminate this, and we want to eliminate, well, it doesn't really matter if that's eliminated or not, but we definitely want to eliminate that. Okay, So what if we put should have got a red marker up. What if we put a stop sign, so to speak? Let's see if I can draw an octagon. Yeah, pretty close, right? What if you put a stop sign right there? It said, nah, you can't go that way. Does that prevent this from happening? Yeah, it does. So it prevents it from happening, so we don't have the danger of breaking our filament, right? It just won't happen anymore. But we still have a problem, and that is that we're, only using half of the voltage waveform. So what if, instead of just putting a stop sign right there, we put a complete circuit in place? And I'm not going to try to draw these things properly because I always get it wrong, and what I wind up with is current just not going anywhere. But what if we could put a thing in place where the electrons will go across the tube in one direction, but we put these things in place that whenever the electrons try to come back across and try to come back, in reverse order, that instead of going all the way to the tube, they'll go through this thing and reroute it and pulse in the same direction.
You like isolate that little part from being able.
Exactly. So now what happens to the negative side of that voltage waveform?
Becomes positive?
It becomes positive, right? It comes up to the top side. Okay, so rectification, to be clear, is changing alternating current to direct current. Okay, we're going to take it a step further and not just change from alternating current to direct current, but we're going to invert that negative side so that now we have two pulses going across the tube, and our output increases by a factor of 2. Okay? So we're a little less efficient than if we didn't do that. Okay? So there's going to be 4 of those in here. This is going to be drawn in a lot of different configurations. The image on the test is not going to be the one that you see on page 109, but all the components are in the same place. So if you know this thing, then you shouldn't have a problem with the diagrams on the test. Okay, and again, really fundamentally the biggest difference is that I'm going to have a line drawn right above the step-down transformer and the MA selector, and I'm going to call that the filament circuit. Right. And another thing is I'm going to divide the main circuit in half right there. This is going to be the high voltage. That's going to be low voltage. That's going to be the high voltage is low voltage. Okay. So if you look on page 109, you see where right before the X-ray tube in the pink part, you see these things that go like this. Right? It's like an arrow, and then it's like that. That's the rectifier. Okay, so the way he's got it drawn, it kind of makes this funny little circuit, and on the top and the bottom, those are the rectifiers. Okay, so those are rectifiers. If you look on page 105, you see them as well. On the diagram at the bottom of the page, you see it also on page 104. So every time you see that, that arrow hitting the dead end, that's a rectifier. Okay.
It's on 102 by itself.
Yeah, on 102 it's just drawn all by itself. So those are they're silicone-based rectifiers. They're semiconductors. They allow electrons to go in one direction, prevent them from going in the opposite direction. So if you see this diamond in here, what you're going to see, I'll go ahead and kind of draw it. But again, I'm going to hit one wrong, and what I'm going to have is like this. I'll have electricity just kind of bouncing around in this one little area right there, and it's not going anywhere. So some diagrams will put all 4 rectifiers just kind of in this diamond little area right there. it's all the same thing, okay? So, really, fundamentally, the only things labeled on the high voltage side on the test is secondary coil, MA selector, which is wired into the secondary coil, the rectifiers, and the X-ray tube, right? Okay, so they should be pretty self-explanatory on the test. You know, everything else is going to be either in the filament circuit or, you know, on the primary side. Okay, so the rectifiers. You know, we got to know the construction of the rectifiers. So they're silicone based, and I mentioned that in when we're talking about semiconductors, a semiconductor, in a lot of cases, is a pretty good conductor that has, or a pretty good insulator, I'm sorry, that has a impurity in it. You remember talking about the water, right? Water is really a pretty good insulator until you introduce impurities, right? You dip your hand down into it and you get zapped, right? Because of impurities in your skin. You introduce oils and salts and minerals and whatever dirt you're hauling around with you, right? So silicone is the same way. So silicone, what we have in our rectifiers is silicone-based rectifier. That's right, purple. And it's divided in half, and one half has the impurities, right? And at one point I think they were using arsenic as the impurity. I don't know that they still are, but at one point they were using arsenic. So, you know, if they come in and demo your room, just don't eat the rectifiers. It could be poisonous. So one is going to be straight silicone, and one is going to be silicone with an impurity in it. Okay, so the side that is just straight silicone, I'm not going to say it has an absence of electrons, but it has no capacity for efficient transmission of electrons. Okay, so I'll refer to that as being electron holes. All right, so it has electron holes. So we're going to say these electron holes. Once we introduce an impurity, be it arsenic or not, then what we're going to have is a situation where we've got at least valence electrons that will travel easily. Okay, so we marry those two together at this junction in between them, and we're going to call this side the p-type, and this the, because those are all negative, n-type. So again, one of the few things in X-ray that actually makes sense. We've got p-type because we have electron holes. Let's imagine that we just don't have enough electrons. And the n-type, we've got too many electrons, okay? So think of it that way. And then think about how charges behave. Okay, so opposites do what? Attract, right. So if I apply electricity going this way, and these are all negative, and these electron holes are then positive, then what's going to happen between the p-type and the p-type rectifier, p-type side of the rectifier, and the electron? They're opposites, so they're gonna attract, right? So what's going to happen is they're all going to charge around this way, and this becomes dead man's land. There's nothing happening there. Nothing goes. So we apply electricity to the p-type side, and we get no flow of electrons. So that's our stop sign up here. I'll never do this properly again. Okay. That's our stop. Stop-ish. Okay, so that's our stop sign up there. Okay, so electrons can't go that way, but if we apply to the negative side, then like charges do what? They repel, right? So I push them this way, and our electron holes go towards the P, and that's what we refer to as the P, N, junction because it's, you know, P-type and N-type. And so we push the electrons. If we flood it with enough electrons, then what we're going to do is we're going to spackle in all these holes. Y'all know what spackle is, right? Take a picture off the wall and, you know, you've got a hole in the wall and you spackle it in. So if you push enough electrons across, they will jump across the p-n junction, and you know, now you've got an overage of negative charges, electrons, and it'll flow in that direction. Okay, so now instead of having a stop sign there, you know, if maybe we'll put our stop sign over here, and we can redirect our electrons through this thing, then when the electricity is trying to come back, and I guess it'll be right here, when the electricity is trying to come back in this direction, instead of going to the anode, it will reroute and eventually make its way back down here, so that we've got two pulses going across the X-ray tube, and we're using the full wave. Okay? So what's the takeaway from this? These are our rectifiers. If you apply a negative charge to the p-type, no flow of electrons. If you apply it to the n-type, then you've got flow. Okay? In that way, if we use 4 of those, then we can not just stop the electron flow, but if we use 4 of them, we can stop it from going to the anode and also invert it so that we can use the full wave. Okay, we're full of things today that actually make sense in X-ray. So if we're only using, you know, half of the wave, let's say we got a dental unit, that's what we refer to as a self-rectifying unit. The X-ray tube becomes a rectifier. As just it doesn't really become the rectifier. It's just that it can't. The electrons have no chance of jumping from anode to cathode. Okay. So in that way, it becomes a rectifier, but you know, they call it a self-rectifying unit. So how much of the wave are we using there? Half. So we're going to call that half wave rectified. Oh, wow, shocking. Okay, so but if we rectify it and we invert the negative side, how much of the wave are we using now? So we're going to call that full wave rectified, right? So any single phase machine that you're going to use is going to be full wave rectified. Okay, now going back to timers, this is why your timers stop every 120th of a second. Because electricity, you know, goes in and out and in and out. How many times a second? 60 times a second, but that's a full wave, right? If we take that negative side and we flip it up, then we're going to have 120 pulses. So every 120th of a second, you can make an exposure. Okay? As single phase machines. We can't use that on most machines, on you know, older machines. I don't even know if they make single phase machines anymore. We still have to cover it. I don't know that they make them anymore. You know, they used to be cheaper than buying, you know, modern machines. But I think it's gotten to the point of diminishing returns where it costs probably more money to make single phase than what it's worth to make single phase. They just can't sell them for cheap enough anymore. So I question whether or not you can buy a single phase. Still have to cover it, but I question whether or not, you know, even a doctor's office can buy it. So then, you know, that'll probably come off the registry at some point. It's still on for now. So what we do have though is that room is three phase and what we refer to as high frequency. Okay, so most of your businesses are supplied with 3-phase electricity. You in your house, you're not, but you know, if you have a 3-phase generator at home, maybe. But at home, you get single phase. But a lot of businesses, it's more efficient, but a lot of businesses get 3-phase power from the power company. So what 3-phase is you've got single phase goes like that, Three phase, you've got three overlapping offset waveforms. And this is harder to draw than what you might think it would be. So one wave starts and the next one comes up. Something like that. And then a third one comes up. Okay. So what you've got then is, this is voltage waveform, so it goes from peak power to minimum power, which actually on single phase is going to be 0, right? The thing with three-phase power is that the voltage waveform, and therefore the eventual power of the X-ray beam, once we create X-rays, never drops to 0. Up here on single-phase, full wave, and half wave rectified machines, it drops to 0 every time a pulse ends. Okay, so pulses end here, but the power never does. Does that kind of make sense? Each pulse ends, but the overall power never does. So what we get off of three phase is a higher average X-ray beam. So for our purpose, a higher average kilovoltage, when we create kilovoltage, we tend to think of KVP. We make KVP, and every photon that comes out of the X-ray tube is that peak energy, and it's not. And we'll talk about that later in the semester. What comes out is, and the amount that comes out at peak power is very, very minuscule, actually. Most of our X-rays that come out of are somewhere around, or the average energy is somewhere around 33% or 1/3 of the peak energy. So anything that we can do to increase that average increases the quality of the X-ray beam, okay? So three-phase power increases that average, so it increases the output. But we still have the problem with, rectification. So what we have here is three phase, that little balloon-looking thing means phase. Three phase, we've got 3 pulses, right? So we've got 3 individual pulses, but if we take the negative side and we flip it up, how many pulses can we get? Yeah, so three phase, we have 6 pulses. So as far as percentage goes, we refer to this as voltage ripple. So as far as percentages goes, if our voltage goes from peak energy all the way down to 0, what percentage of voltage ripple do we have with single phase machines, be they half wave or full wave rectified? It goes all the way from the highest down to zip. 100%. Was that, I heard, but I couldn't make it out. 100%, it's 100%. Regardless if this is what we're doing or this is what we're doing. Okay, it's 100% voltage ripple with any kind of single phase machine. Even with three phase unrectified, it's not 100%, right? But by the time we flip the negative side up, what's going to happen is all of these valleys are now going to be spackled in even more. And so three phase 6 pulse is going to give us about 14% voltage ripple, meaning that the peak energy doesn't drop more than 14% throughout the exposure. So your KVP, your average KVP increases. Okay, everybody with me so far? Because I'm about to introduce 2 things that aren't going to make any sense at all. All right, the first one is, you don't have to know how this works, and I'm not even going to cover how this works because it's just circuitry voodoo, but we can bounce those 6 pulses kind of back and forth a little bit and actually get 12 pulse 3 phase. yeah, I agree. It's like 3 phase times 2 equals 12, whatever. Okay, but we can do it. And once that happens, then the voltage ripple drops to 3%. Okay, so what happens there? We get a higher average, right? So our beam energy doesn't drop. Say we set 100 kVp, it doesn't drop more than 3% on those peak energies.
So your lowest is 7 kVp.
What's that? Yeah, so it might drop to 97. Yeah. Okay. So now here's the other part that doesn't make any sense. So we go from single phase to three phase. We're going to get a higher average, but when we went from unrectified to rectified, we also got a higher output, meaning mass essentially, right? So we go from single phase to three phase, you would expect that our output would increase by a factor of? Yeah, you would think so. It doesn't. It's a factor of 2. Okay? Yeah, I know. You look like you just smelled Limburger cheese. It's like,
Yeah.
what? Yeah, it's 2. It's a factor of 2. Okay, so what's a practical application for this? Let's say you're working in a clinic that has a 3-phase machine and a single-phase machine side by side. And you make an exposure on a 3-phase machine. Let's say, since we're going through C-spines, or we just covered C-spines, let's say you're shooting an AP C-spine, AP axial C-spine, AP C-spine, and you used 75 kVp at 12 mass on 3-phase machine. Okay, what's your output on a single-phase machine compared to 3-phase machine? It's half. It's half, right? So if you use that same technique in the single-phase room, what is your index number going to look like? It looks like you underexpose the patient by exactly half. So if you take that technique and apply it to a single-phase room, what are you going to have to do? Double your mass. Okay, so 3-phase to single-phase, you got to double your mass. If you go from single-phase to 3-phase, you have to cut your mass in half. Okay? So better output, better average, still got 3% voltage ripple. So the next and most common type of generator that we use is what we refer to as a high frequency generator. Okay. So purpose for a high frequency generator is try to get rid of that 3% in as much as we can. And this is kind of the best explanation that I've found for how this works. Okay. Let's say we got 3% ripple, voltage ripple, off of a 12 pulse. Okay. So let's say we use the basic circuitry of the 12 pulse and we account for that 3% voltage ripple. So that you set a technique of 100 kVp on that 3-phase machine, and you can get, at the bottom of that, voltage waveform, 97. That's still pretty good, right? He's still penetrating anything the patient has, but it's still a 3% drop. So what if then we did this? You set 100 kVp and it actually gives you 103. Well, if it gives you 103, but what we then do is come through and we knock the peaks off at exactly 3%. What do I have? 100 kVp. And what's our voltage ripple?
0.
Very close to 0. So it's less than 1%.
You knock that
Okay.
margin of error out.
Exactly. Right. That's what they refer to as a chopper circuit. Not chopper, but it chops the top off of the voltage waveform, right? It's a chopper circuit. And that's the circuit that you can actually hear sometimes when you make an exposure. If you're working in certain high frequency rooms, you make an exposure and you hear this whining sound. And it's not the beep at the control panel, it's in the room with the x-ray tube. And it's actually coming out of the generator box and it kind of goes zzz, like that. They've insulated those to the point that you don't hear it nearly as much as what you used to, but when they first started coming out with those, it sounded like something bad was happening in an x-ray room. It was very audible. So that's high frequency. Okay, so that's if like our brand new machine up in the lab is high frequency. Probably every machine that you're working with is high frequency. Okay. So all this other stuff is probably eventually gonna come off the registry, it's just not yet. The registry is always a little behind what the technology, and even the textbooks in a lot of cases are kind of behind what the technology is, updating with. But we've been at high frequency for a lot of years. At least single phase should be gone. It really should. Okay, so any questions on all that? Yep.
So you're saying that pretty much all the X-ray tubes that we're using today are in three-phase?
They're at least phase, probably high frequency. Yep, yep. It's wild too that okay, so our lab over in Pirtle, before we moved into this building, before we built this building, it was a single phase machine, and the generator, the high voltage transformer was in a box almost as big as that podium. I mean, this thing was, 2.5, 3 feet high, and it was cube, so it was pretty much 3 feet in every direction, right? And they're getting ready to put this one in, and if you look at the back of the room on the right-hand side, there's a box that's back there that's probably, I don't know, it may be 3 feet long and 3 feet tall, but it's only about a foot wide. Inside that box is a thing that's about the size of a 2.5 gallon paint can. That's your generator. That's your high voltage transformer. In that little bitty thing, where they used to be massive, they're tiny now. And they can put those actually in a false ceiling. They can put them inside of the overhead crane system. And they just take up, the footprint is so small on a high frequency transformer, high frequency generator that they can put them anywhere. They can go inside the X-ray unit itself. So pretty wild, pretty wild. We've got technology and we can create a much more efficient, high average, X-ray beam, and the circuitry has shrunk to nothing. It's tiny. Okay, so any questions on those? So we talked about self-rectifying tubes, we talked about single phase, 100% voltage ripple on both of them, full wave and half wave rectified units. We talked about 3-phase, overlapping pulses, rectified, you can get 6 to 12 pulses, 14%, 3%, less than 1% in high frequency. So it's near constant potential. Okay, capacitor discharge units. Again, something that probably should come off the registry. Well, maybe not, maybe not. So, have you worked with a portable machine that you had to plug in, not to charge the batteries, but to make an exposure? No? Okay, they're out there. I think most of them actually carry around a generator inside of them to take voltage and make kilovoltage. Austin, I was wrong about the battery thing. I think there is a transformer in portables, in all portables. I think even battery powered portables have to go from DC to AC back to DC. I don't think you can get that any other way. So I was wrong. You can tell the top, if it's got batteries or if it doesn't have batteries. First off, if it doesn't have batteries, you got to plug it in to use it. If it does have batteries, you can tell as soon as you get on the elevator. Right? Exactly. Everybody freaks out when you get on the elevator because it dips, right? That's because batteries are heavy. If you've never picked up a car battery, car battery is probably, 60 to 80 pounds. They're heavy. And that portable is full of them. Don't run over your foot or anybody else's foot with a portable. I did that kind of down the soft tissue on the side of my foot. I had a blood blister from my heel all the way to my toes. It just got the soft tissue. They're heavy. All right, so be careful, don't run over yourself. A capacitor discharge portable unit might be one where you plug it in, and think of capacitor discharge as being kind of like a single shot battery, okay? So a battery, what you've got is, you know, a thing that stores electrons. And a capacitor discharge is kind of the same thing. Only it stores energy for a single use, right? So what you have then in a capacitor discharge is kind of like a, you know, almost like a semiconductor, in that you've got two things where you can store electrons, or one thing where you can store electrons. And let's say it's kind of like a cathode and an anode type situation. So what you've got is all these electrons, you plug it in and you kind of charge your capacitor up, and that's a capacitor, is capacity to store electrons, right? So you got your capacitor charged up because you plugged your portable in, and you got all these electrons, but you've got something, be it a distance or something, that prevents those electrons from jumping this gap. So once you get the charge that you need and that you want, then you can break down that insulation in between them, that electrons can jump across and make your exposure. Okay, so then they travel across that, and that's your discharge. Your capacitor is building up the charge, the discharge is allowing the electrons to jump across. As a capacitor discharge type X-ray unit, never worked with one, and they used to be fairly common in portables. And how they work then is where your falling load generator, if you remember back to that, because I'm bringing that back up because you might have a tendency to confuse the two. Falling load generator, the MA drops throughout the exposure, right? The MA starts very high and it drops throughout the exposure. With a capacitor discharge, what you do is, let's say you set 100 kVp, and the kVp starts at 100, but as we lose electrons, the kVp drops throughout the exposure until it gets to either the end of the exposure, or it gets, you know, low enough that it just is ineffective anymore. Okay, so capacitor discharge, what drops? kVp, right, as opposed to falling load generators, MA drops, right? So purpose for falling load generator is shortest possible exposure time. Purpose for capacitor discharge is just to confuse you. Again, something else I think probably should come off the registry. Probably shouldn't be in the textbooks anymore. Okay. So voltage ripple was on the next page. Power rating is really the only thing that we've got left. So power, you know, we're dealing with electricity, and what's electric power? How do we calculate electric power? It's measured in watts, right? And that is voltage times amperage. So power rating then in our X-ray unit is just that. So it's, you know, it's amps times volts, but it's going to be very specific. So if you look on page 108, you'll see it. So it says that power rating is the maximum tube current, that's your MA, possible at 100 kVp and 100 milliseconds. So they're going to be measured in kilowatts, not just watts, but kilowatts. And, you know, maximum tube current at 100 kVp, 100 milliseconds. That's the power rating of your unit. So you can calculate the power rating for whatever reason. You know, going to clinicals tomorrow and Monday. Play with that if you want to, as if you would want to. Right. So, any questions? Okay, so I've started a review for the positioning, and I'll get it finished up and get it posted today, so that you'll have that before the T-spine and L-spine lecture. I've gotten all the way through C-spine. That's not as extensive as the one on lower extremity. Goldie also put some stuff into Canvas, and those are in your lab shells. Okay, I don't know that Mindy had it or not. If not, I'll see if I can copy them over and get those into hers as well. What else? I would recommend going ahead you know, we're past midterm now. I would recommend that you go ahead and start looking at the final review. What's our time? Oh,
Let's go 20 minutes.
Yeah. So let me show you real quick the final review, because I don't want you to be kind of confused with it. It's pretty extensive, but there's a lot of redundancy in it. And how I made this review was essentially everything that you needed to know about this class is in there with short explanations or just, you know, kind of as topics that you need to understand. And it is in your 2309 class. This is the physics review. So again, it's just a short explanation, a lot of topics. So, you know, alternating current, why do we have to have alternating current? It's required for transformer operation, so we have to have it all the way up to the rectifiers so that, you know, the rectifiers change it to direct current so we don't destroy the X-ray tube. So, you know, read through this, and again, there's going to be some redundancy in it. You know, there's like MA and mass. So just understand, when I wrote this, it wasn't that, oh, I didn't write that, you know, I didn't include that before. You know, I understand that there is some redundancy, and I left it that way because, like, if I'm talking about, I don't know, MA all by itself, well, I got to mention that MA is half of mass, which is time, right? And I get down to timer, you know, it's fairly alphabetical. I get down to timers, I've got to mention MA, you know, just so that you are reminded that time is the other half of mass, right? So you're gonna see some redundancy in this. So this is pretty extensive. And let's see, how many pages is this?
7.
7, okay, thank you. So we